Imagine looking up into a night sky so ancient that its darkness is crisscrossed with invisible highways, used for ages by wandering cosmic bodies, and then discovering that one of these travelers is about to come barreling through our own solar system, following a path uncharted and inexplicable. That's exactly the situation we find ourselves in with 3I Atlas, sometimes referred to as 3 Atlas, an object so unlike anything we've observed before that it's begun to bulldoze our notions of what passes for normal among space visitors. Not just another icy snowball, 3I Atlas is an interstellar interloper, a migrant from beyond the gravitational reach of the Sun, and it's now rapidly approaching its perihelion, the moment it passes closest to the Sun, around October 29th. The very label we give this object is itself a subject of debate. While some astronomers hastily define it as a comet, that word feels increasingly inadequate. There are elements of cometary behavior in its composition and obvious coma, of course, but this is no ordinary member of the family. In fact, as more data pours in, that family resemblance becomes increasingly strained. The truth is, every known object in our solar system, comet, asteroid, centaur, Trans-Neptunian world, even those weird oblong dwarf planets, follows certain chemical and physical patterns. 3I Atlas, by contrast, is like the strange cousin whose arrival at the reunion makes everyone else look conventional. At present, our best speed measurements tell us that 3I Atlas is hurtling through space at an astounding 60 kilometers per second, and as it reaches perihelion, that speed will increase to 68 kilometers per second. To place that in context, imagine if you could circle Earth at the equator in a little over 11 minutes. No other object speeding through our inner solar system even comes close to matching that pace. While scientists have put its size somewhere on the scale between a mere 200 meters up to a colossal 50 kilometers across, the definitive answer remains elusive. That's not just a trifle, it's a pivotal mystery, as a 50-kilometer diameter object moving at this speed would make any planetary impact far more than a mere extinction-level event, spelling catastrophe on a scale we don't want to contemplate. But before you reach for your handy asteroid panic button, it's important to remember that, so far, its trajectory keeps it at a distinctly comfortable cosmic distance from Earth. But the real marvel isn't just 3I Atlas's speed or potential size, or even its origin from interstellar space. It's what it's doing right now. For months, astronomers have been mapping its changing coma, that cloud of gas and dust whipped up as sunlight warms the surface of its nucleus. And what they're finding throws a wrench into everything we thought we knew. Using a technique called polarimetry, researchers have been tracking the changes in how 3I Atlas interacts with light, in particular, how that light is polarized. Now, just like sunglasses can reduce fierce glare by filtering light that scatters in certain directions, polarimetry allows scientists to see how sunlight, hitting clouds of dust and gas, gets sorted by the tiny building blocks in the coma. But it goes much deeper. The degree and orientation of this polarized light act as a diagnostic tool, revealing the hidden architecture of material around the nucleus. This isn't just a rough snapshot or fuzzy image. By measuring these polarization shifts, we can infer things like the size and shape of dust grains, how they're structured, and even the degree of plasma present. Across July and August, the data revealed that 3I Atlas's coma wasn't just growing, it was becoming layered and structured in a way we've never seen before. What did the measurements show? In the most striking cases, negative linear polarization values reached an astonishing 6 degrees at a mere 7 degrees phase angle, the angle between the Sun, the object, and us as observers. That's not subtle. For typical solar system comets, this polarization flip from negative to positive occurs around 20 degrees, and the extremes are nowhere near as pronounced. Even some of the strangest comets on record, like Halley's Comet and the rare outlier Hale-Bopp, didn't show such a rapid or intense inversion. But in 3I Atlas, That flip came much earlier, at only 17 degrees, and to values that fell far outside the normal spectrum. For comparison, most run-of-the-mill comets and asteroids display these swings as gentle slopes. 3I Atlas, by contrast, takes a wild, unexpected turn with numbers that simply don't fit established categories. But let's not skate over what polarization means here. Picture a wave of sunlight streaming across the galaxy. Every photon, every packet of light, carries not just energy, but directionality when it encounters dust or molecules in the coma. Its electric and magnetic fields interact. Unpolarized sunlight, the light that reflects straight from the sun, bounces in all directions. But once it scatters off those dust grains, it gets nudged into certain alignments. Scientists measure this by capturing light and comparing how much of it vibrates parallel versus perpendicular to an imaginary plane formed by the sun, the comet, and us as the observer. The greater the difference, the stronger the polarization, and that difference encodes rich physical information: dust size, grain shape, composition, and, crucially, plasma characteristics that can't be measured any other way. To further visualize just how strange this is, imagine looking at a set of time-lapse photos of 3I Atlas taken over late July to late August. What starts as a simple, rather normal-looking coma rapidly swells to about half the sun's diameter, if you can conceive of that, and acquires rings and double layers in its polarization map. The center remains almost neutral, close to zero polarization, suggesting evenly distributed dust. But the further out you go, the more pronounced the positive and negative swings. This isn't just random noise. These concentric regions echo well-known plasma physics, specifically something called a double layer. In laboratory plasmas and space environments, double layers form when regions of opposite electric charge align in close proximity, creating an electric field strong enough to accelerate particles and, critically, to shape entire clouds of matter. That's exactly the kind of pattern researchers see in some of the polarization heat maps from 3I Atlas. A core of balance ringed by shells of heightened and opposed electrical activity. It's as if we're watching not just dusty gas, but electrically alive matter, woven by unseen electromagnetic forces. Here lies a genuine aha moment for planetary scientists. It's not just about the size of the coma or the speed of the nucleus. It's the rapid and evolving complexity of these plasma structures, which stand apart from anything we've watched in even the weirdest solar system comets or asteroids. The data, published in a recent paper entitled Extreme Negative Polarization of New Interstellar Comet 3I Atlas, doesn't shy away from this implication. The object, the study suggests, could represent an entirely new class of small planetary bodies, neither comet nor asteroid nor dwarf planet, nor exactly like anything previously cataloged. Extrapolations using known mathematical models align these findings not with existing comet groups, but with the rare and shadowy population of Trans-Neptunian objects, bodies far beyond Pluto that experience constant cosmic ray bombardment and preserve the chemical fingerprints of the early interstellar medium. And yet, even these distant cousins only resemble 3I Atlas's behavior in certain respects. The negative and positive polarization values in the phase angle diagram exist mostly as mathematical predictions for those outer solar system objects, not as directly observed reality, but as if strange light polarization weren't enough, something even more visually spectacular has begun to happen. When ground-based observers, capitalizing on the natural darkness provided by a lunar eclipse on September 7th, turned their telescopes toward 3I Atlas from the Kalahari Desert in Namibia, they expected to see a faintly red object in keeping with what previous spectrometry had shown. Instead, their sensors lit up with an unmistakable green glow. Now, here's where the story kicks off another gear. Normally, when we spot a green comet, we know the culprit, diatomic carbon, or C2, which fluoresces at a very specific wavelength, 518 nanometers, when energized by sunlight. It's a staple feature of cometary chemistry, responsible for some of the most striking comet tails in photographic history. But in the case of 3I Atlas, readings from July and August indicated a marked depletion of C2 in its chemical makeup. Its coma is dominated instead by carbon dioxide and water ice, more reminiscent of a frozen Trans-Neptunian object than a textbook comet. If C2 isn't available to produce that emerald glow, or at least wasn't before, what is causing the spectacle now? It's a question scientists are still racing to answer, and it comes packed with fascinating hypothetical options. Maybe, just maybe, as 3I Atlas plunges closer to the Sun, exotic chemistry previously dormant is being woken up, activating new emissions or causing hidden stores of C2 to be released. Or perhaps another molecule entirely, one we're less familiar with in these settings, is stepping up, producing green light through a different mechanism. If this is true, and the green glow emerges through unfamiliar chemistry, 3I Atlas may be giving us a window into the sorts of reactions that shape planets and comets around other stars, far beyond our own solar system's norms. Let's not forget, surface spectrometry in its earlier approach showed that 3I Atlas was a deep, weathered red, a color typically acquired as cosmic rays bake the ices on a body drifting for eons through interstellar space. That signature, overtaken now by an abrupt green beacon, speaks to a planetary biography with more twists than we can yet document. Pulling back from the chemistry, let's take a look at the journey through our solar system, both for context and for the very real stakes involved. Using real-time web tools like the Sky Live, astronomers have tracked 3I Atlas as it slices through the inner planet's orbital territory. By early September, it had crossed into the asteroid belt, on its way to a close approach to Mars on October 3rd. Never close enough for true danger, but within roughly 0.2 to 0.3 astronomical units. That's the Earth-Sun distance, about 150 million kilometers as your yardstick. There's some tantalizing hope that the reconnaissance probe currently orbiting Mars may be able to snap a close-up, high-resolution image of the nucleus, providing a concrete answer to its true size and composition. For now, the best estimates derive from how brightly its coma reflects sunlight across various wavelengths, a method that is notoriously tricky, as it depends on assumptions about the object's albedo or reflectivity. Get that wrong, and your diameter estimate could be off by orders of magnitude. But with a direct measurement possible from Mars's orbit, we may soon have clarity. As October marches on, 3I Atlas will continue its breakneck course, meeting Earth's orbit at superior conjunction when the object is on the opposite side of the Sun from our vantage point, around October 21st. Our planet keeps a respectful distance in this cosmic dance. Not only does this avoid any hint of collision danger, it also means we won't get the best possible view, just as the comet's sun-facing activity is likely to spike. Its perihelion, the solar system's ultimate close encounter, comes on October 29th, when its speed reaches that staggering 68 km, and its plasma-rich coma will be at its most energized. There is reason to suspect that such a massive, freshly ionized envelope of plasma, moving at unprecedented velocity, could actually provoke solar reactions of its own, potentially sparking solar flares or triggering heightened space weather as this alien matter mingles with the solar wind. X-class flares, the most powerful category our Sun produces, are not out of the question as a consequence of this fleeting yet huge interaction. In March, 3I Atlas is expected to zip by Jupiter, completing its dramatic sojourn through our neighborhood before vanishing again into the abyss of interstellar space. The implications of 3I Atlas's journey span the entire spectrum of planetary and astrophysical science. To see these polarization patterns, extreme negatives, abrupt inversion at low phase angle, evolving double layers, is not just to log another data point, but to encounter a fundamentally different set of physical processes at work. To watch its coma grow to half the sun's size and acquire organized plasma architectures is to peer into a new world of interactions between light, matter, and magnetic fields. To see a color-shifting, green-glowing, fast-moving object of indeterminate class and origin is to be reminded that our own solar system may just be one more collection of cosmic oddities, and that the universe's inventory of planetary body types is far from complete. Even more, the entire scientific process unfolds right in front of us, looped into ongoing research. The paper, Extreme Negative Polarization of New Interstellar Comet 3I Atlas, lays out both the findings and the riddles, spaceweather.com's continuing documentation, along with the regular updates from datasets around the world, give this story a living pulse. As polarimetry continues to decode the architecture of the coma, as each spectral measurement is added to the timeline, and as every pixel from ground and spacecraft imaging is squinted at for answers, our understanding evolves in real time. The next few months, the era of 3I Atlas, could yield the sort of discovery that forces textbooks to be rewritten, not just updated, about what kinds of small planetary bodies exist, how plasma and chemistry operate on an interstellar interloper, and how cosmic travelers sculpt and are sculpted by encounters with our sun. And so, as you watch the night sky in the coming weeks, take a moment to marvel at what's passing overhead. Not just a comet, not just another asteroid, a visitor from the galactic dark, one that bears stories from before our sun even formed, and whose own story, unfolding right now, is rewriting what it means to be a planetary scientist, an astronomer, or simply a curious human tethered to Earth yet staring outward in awe. The data may at times seem daunting. Percentages and angles, polarized light curves, chemical emission spectra. But behind every number is a revelation, and behind every observation, an echo of vast processes that shaped our system and perhaps seeded the existence of worlds unknown. If you want to follow this cosmic detective story as it unfolds, each new observation could be a twist. Will the green glow intensify? Or will another unexpected color break forth? Will the Mars orbiter offer up a direct image that resolves the object's size debate? Will passing near the sun trigger the greatest solar flare in decades? Every week, new clues emerge, and with each comes the tantalizing possibility that we're inching closer not only to explaining the enigma of 3I Atlas, but to glimpsing the diversity and wildness of worlds beyond our own. Stay with us, subscribe if you haven't, to remain at the very edge of what's known. And as we follow up with data, analysis, and piercing scientific curiosity, remember that the universe is always more surprising, more intricate, and yes, more mysterious than we've ever dared imagine. The best discoveries may still be ahead, the answers still hiding in the polarized shimmer or sudden emerald flash of an interstellar passing in the night.